Thank you so much. Let me take this opportunity to welcome you to our physics lesson, Form 2. We are going to look at the waves, and specifically on waves basing on our objectives. We shall look at the following in our objectives. Number one, that is, we shall focus on the phase and the phase difference of a wave. We shall be focusing on the phase and the phase difference of a wave. And then we shall look at the relationship between wavelength, speed, and velocity and frequency. We shall look at how the equation that relates wavelength, speed, and frequency of a wave. So, in case you have any question as we proceed with the lesson, you can be able to ask. That is on the way. So, I want us to begin by looking at the phase and phase difference of a wave, and for us to be able to understand, that is the phase and the phase difference of a wave, there are some factors that we need to consider. We began by looking at the characteristics of a wave motion. Among the characteristics of a wave motion, we say that a wave is made up of the amplitude, and the amplitude is the maximum displacement of a wave on either side. We also say that a wave is made up of frequency, and frequency was defined as the number of oscillations made by a wave in 1 second. We also said that a wave has wavelength, and wavelength is written using the sign lambda. This is the distance that is covered, or the distance that a particle travels for it to cover one complete oscillation. We also talk about the period, and the period is written in capital T. Period is the time taken for a particle to make one complete oscillation. So those are the characteristics of a wave motion. So by looking at the wave motion representation using the diagram, we can be able to see that waves have amplitudes, they have certain frequencies, they travel at a given period, and they also have wavelengths. These waves can be looked at in terms of two factors. Number one, we shall be looking at these waves in terms of the amplitude, that we have the waves that have the same amplitude but different frequencies. We have waves which have the same amplitude but different frequencies. An example of the diagram that we have illustrates the waves which have the same amplitude but different frequencies. So if you look at this wave, you'll find out that the maximum displacement of each wave on either side is at the same level. If you look at the wave that is drawn in red, we also have another wave which is drawn in blue. These two waves have the same maximum displacement on either side, meaning that the waves have the same amplitude, but they also travel at different frequencies. In the same case, I want us to consider the identical pendulums, where you have two pendulums. A pendulum is a bob mass, which is tied using, or which is suspended using a string and allowed to swing freely. So we are told that a pendulum moving at a speed more than the other, but moving in the same direction, then the waves are said to have different frequencies but the same amplitude. So this gives us the correct, or the illustration of waves with the same amplitude but different frequencies. And here you are told that you have two pendulums. These two pendulums are moving at different speeds, but they are moving towards the same direction. Therefore, the pendulums are said to have the same amplitude but different frequencies. So also, if we proceed, Rachel is not seeing the slides. I hope others, you are seeing them. I'll also confirm mine if I can be able to see. Yes, Rachel, the slides are visible. They are visible. Yes, you can check on your Okay, nobody is seeing the slides. Okay, I'll check on them again. I'm sorry for those who are not seeing the slides. Okay, you can check once more because for me, I can be able to see them. What about you? You can check once more. Yes, are we seeing the slides now? Yeah, it's okay. Thank you. Sorry for those who are not seeing the slides. So we can be able to proceed. Check once more because for me, I can be able to see them. So I'll go back to my initial explanation. That is, we are told that waves, the waves and the waves characteristics, we have also spoken about them, that the waves have different characteristics. They possess amplitudes, they travel at a given frequency, they travel covering a certain period, and they also have wavelength. So we are saying that the waves can have the same amplitude but different frequencies. We can have the waves having the same amplitudes but different frequencies. And as you can be able to see on the diagram, I have two waves which have been drawn, two wave motions which have been drawn using different colors. So you can be able to see that looking at these two wave motions, they are drawn so that the maximum displacement on either side is at the same level. But looking at the way they travel, you'll find out that the wave in blue travels faster than the wave in red. So, and in this case, through an illustration, we're told that consider the identical pendulums. So that we have two identical pendulums. These two identical pendulums have been suspended freely and then they are allowed to swing. You'll find out that when these two pendulums are moving in the same direction but at different velocities, then the waves are said to be at different frequencies but on the same amplitude. And this is the statement that we have here. A pendulum moving at a speed more than the other but moving in the same direction, then the waves are said to have different frequencies but the same amplitude. So that is the first point that we wanted to look at, waves with the same amplitude but different frequencies. On the other hand, I want us to look at the waves with the different amplitudes but now the same frequencies. The waves with the different amplitudes but now the same frequencies. At this point, looking at the two waves, their maximum displacement on either side should be different. And as you look at the two waves, we have the wave motion represented in blue and the wave motion represented in red. You can be able to see that their maximum displacement on either side is different, such that the wave motion in red is displaced far away as compared to that in blue. So using this diagram, you can be able to illustrate that the two wave motions are traveling at different amplitudes but at the same frequencies. Therefore, after or having looked at the waves having the same amplitude and different frequencies, and the waves having the same frequencies but different amplitudes, it can be very easy now for us to look at the phase and phase difference of a wave motion. So we can talk about the waves which are on phase and the waves which are out of phase. So I want us to begin by looking at when a wave is 90 degrees on phase. When a wave is 90 degrees on phase. So how do we draw that representation? So our initial wave is in red. So we want to use that wave that is drawn in red so that we can be able to draw another wave which is 90 degrees on phase. So that wave, I happened to draw it in blue. So as you can be able to look at that wave, these two waves should travel at the same frequency. I want you to compare the frequency of the two waves. The two waves are traveling at the same frequency, but the amplitude of the wave in blue is half to that wave motion in red. So this situation is explained that the wave is 90 degrees on phase. That wave in blue is 90 degrees on phase, meaning that its amplitude is half the amplitude of the initial wave, and the two waves are traveling at the same velocity. I hope you are together up to there. In case you don't get anything, you can just ask the question. I'll be able to respond to it. As we move along, we have been able to look at the waves which are 90 degrees on phase. Now, I want us to look at the wave which is 90 degrees out of phase. 90 degrees out of phase. Our original wave is in red. So we are drawing another wave in blue, which is 90 degrees out of phase. So when we say that the wave first is 90 degrees, the amplitude should be half the amplitude of the original wave motion. When we say 90 degrees, it means that you reduce the amplitude by a half. That is the first thing you're supposed to do. And then number two, the two wave motions should be traveling with the same frequencies. As you are able to see the wave motions here, the two wave motions are traveling with the same frequencies, but now they are out of phase. Out of phase means that they are traveling in different directions. So looking at the wave motions, you can be able to see when the wave motion in red goes up, the one in blue goes down. That means the two waves are out of phase, but the wave in blue is 90 degrees out of phase. Reason being, the amplitude is half the amplitude of the original wave. The two waves have the same frequencies, and the two waves are moving at the same frequencies, and they are traveling in different directions. So that is when we say that a wave is 90 degrees out of phase. I want us now to look at when a wave is 180 degrees on phase. So 180 degrees means that the amplitude should remain to be the same. When we talk about 180 degrees, it means that the two wave motions should have the same amplitude. The amplitude does not change. So I want you to look at the maximum displacement of the waves on either side. You can be able to see that they have been displaced at the same level, meaning that the two waves are at 180 degrees. Then why do we say they are on phase? They are on phase because the two wave motions are traveling in the same directions. Therefore, these waves are said to be 180 degrees on phase, because the two wave motions are traveling in the same directions with the same frequencies and the same amplitude. And at that point, we say that the waves are at 180 degrees on phase. Apart from 180 degrees on phase, I want us now to look at when the wave is said to be 180 degrees out of phase. When do we say that a wave is 180 degrees out of phase? First, I began by saying that when we talk about 180 degrees, this means that the amplitude remains to be the same. The amplitude does not change, the amplitude of the wave. But when we talk about out of phase means that the wave motions are traveling in different directions. The wave motions are traveling in different directions, but with the same frequency. So looking at the two waves here, they are 180 degrees out of phase because the two waves have the same amplitudes. They are traveling at the same frequencies, but their amplitude remains to be the same. So the two waves are said to be 180 degrees out of phase. So when we talk about the phase and the phase difference, at this point, the frequencies of the wave does not change. When you have seen that when we talk about the waves on phase and the waves out of phase, all these waves maintain their frequencies in that the frequencies remain to be the same. You have also been able to notice that what changes is the amplitude. When you talk about the waves on phase and out of phase, number one, what changes is the amplitude and the direction in which the waves travel. When we say they are on phase, these waves will travel in the same direction. When the wave motions are out of phase, then they travel in different directions. When we talk about 180 degrees, then the amplitude remains to be the same. But when you talk about 90 degrees, then the amplitude is halved, or half of the amplitude is taken by another wave. So reaching at that point, then it can be very easy for us to understand the phase and the phase difference of a wave. So reaching up to that point, if we have any questions concerning the phase and the phase difference on the waves, you can just ask as we proceed. Maybe you can put your question through writing. I can be able to see it, and also you can decide to unmute the mic so that we can also be able to communicate. It is also going to be okay. After looking at the phase and phase difference of a wave, finally we shall look at the relationship between the velocity of a wave, the frequency of a wave, and the wavelength of a wave. I want us to look at the relationship between the velocity of a wave, the frequency of a wave, and the wavelength of a wave. So how does this relationship come? If you look at, we are told that suppose the period of a wave is t. Suppose that the period of a wave is t, and the distance covered by a wave is lambda. Lambda is a wavelength, and we defined it as the distance covered by a particle in one complete oscillation. Lambda, it is the wavelength. The period by this particle is t. Therefore, how do you calculate the velocity? Velocity is the speed of a wave. Velocity is given by the distance covered by a wave over the time taken by a wave. Therefore, if the velocity is v, then the distance covered by a wave is lambda, which is wavelength, over the time taken by a wave is t, which is the period. That is from the normal formula of linear motion. Speed is given by distance over time. So we are replacing the same when working out the relationship here in waves, that take the velocity to be equivalent to the distance by the wave over the time taken by the wave. And the distance by the wave is the wavelength, which is lambda. The time taken by the wave is called period, which is t. So that v is equals to lambda over t. But from the calculations of wave motion, if you want to get the frequency, then t is given by 1 over f. T is given by 1 over f. Meaning that in the formula where we have velocity is equals to lambda over t, replace the value of t with 1 over f to get that v is equals to lambda over 1 over f. V is equals to lambda over 1 over f. Summarizing that equation by multiplying the value of lambda by f, you'll find out that v is given by f lambda. V is given by f lambda, where v is the velocity of a wave, f is the frequency by the wave motion, and lambda is the wavelength of the wave. Therefore, this equation v is equals to f lambda is giving us the relationship between velocity of a wave, the frequency of a wave, and wavelength of a wave. And using this equation, you can be able to calculate the velocity, frequency, and wavelength of a wave. So apart from that one, you can also be asked to explain the variation of frequency and wavelength. Or how can we explain the variation of frequency and wavelength? The variation of frequency and wavelength is simply the relationship between wavelength and frequency. What is the relationship between the frequency and the wavelength? And using a graph, when we plot a graph of frequency against wavelength, we are going to have our frequency in the y-axis and our wavelength on the x-axis. Comparing the two, we are going to obtain our graph in the sketch, as we can be able to see. So that is the sketch of the graph that we are going to obtain when plotting the graph of frequency against wavelength. So what relationship are we getting? In that equation v is equals to f lambda, we have plotted frequency against wavelength. Therefore, in the equation V is equals to F lambda, you can be able to write it in form of an equation of a straight line. That is in form of Y is equals to mx plus c. So that you can be able to see the relationship between frequency and wavelength. How is the relationship? You'll be able to find out that when the wavelength increases, the frequency reduces. And looking at the diagrams that you have been able to see when you are looking at the phase and the phase difference, you'll be able to notice that when the frequency increases, the wavelength reduces. When the wavelength increases, the frequency reduces. Let me take you to one of the diagrams so that you can be able to see. The first diagram, it is there. You can be able to see that the wave that has a higher frequency is the wave motion in blue here. You'll be able to notice that it has a higher frequency, therefore the wavelength is very small. But look at the wave in red. It has a smaller frequency, but now the wavelength is large, meaning that when you increase the frequency, you reduce the wavelength. And that is why, looking at the sketch of the graph where frequency has been plotted against wavelength, you can be able to look at the relationships of wavelength and frequency, whereby when the frequency increases, you'll find out that the wavelength of a wave is reducing. So that explains to us or gives us the relationship between frequency and the wavelength. Finally, we have the little quiz for you here that calculates the frequency of the wave. Calculate the frequency of the wave. We have the question there on the screen. You can be able to see it. So if you have any question, this is the time that you can begin writing to me your questions. We have some minutes before we end the lesson. I already have one of the questions that has been sent to me by Rachel. Rachel is asking, how do we know the frequency and wavelength? How do we know the frequency and the wavelength? Thank you so much, Rachel. That is the question that we explained. That is when we are introducing waves. Remember that when we talk about phase and phase difference, that is the second lesson after the first lesson that we looked at how you can be able to identify the frequency and the wavelength. So I said that frequency is the number of oscillations made by a wave in 1 second, or the number of oscillations which are made by a particle in 1 second. So look at the number of oscillations in a wave. For example, in a wave that you can be able to see there, which wave has so many oscillations? You can be able to see that the wave in blue has so many oscillations. Or in simple words, I want you to look at which waves moves is making so many movements up and down. That is the waves that has a higher frequency, and this is the wave in blue. So the number of oscillations that are made by a wave in 1 second is what we call the frequency, and the wave in blue here, you can be able to see that it has a higher frequency. And then I want you to look at the wave in red. The number of movements made by that wave, they are very few. So we say that it has a lower frequency. So that is how you can be able to look at, to determine the frequency of a wave using the diagram. You look at the number of oscillations, or in simple words, I've told you, look at the number of motions that are made by a wave when moving up and down. You'll find out that the wave in blue has so many movements up and down as compared to the one in red. And the wave in blue is said to have a higher frequency than that in red. So on frequency, Rachel, that is how we can be able to compare. Then when to determine the wavelength, we talked about the crest and the trough. When you look at this wave motion, it climbs. When it climbs, it forms something like a hill. That is called a crest. Then when it drops downwards, it forms something like a valley. That is called a trough. So when you count one hill and one valley up to where it ends, or look at the first point where these two waves meet on the x-axis, that is what we call one complete oscillation. For a blue wave, look at where it meets the red wave motion. That is what we call the the wavelength. So that is how you can be able to measure the wavelength. So when you complete when you count the number of oscillations, you count the number of crests and troughs. So when we have one crest and one trough, that is one complete oscillation, and that is what we call a full wavelength. Then count another crest and another trough, that is another full wavelength. So that is how you can count the number of complete oscillation. A number of one complete oscillation is equivalent to one wavelength. So I hope up to there, Rachel, you are okay. We also have another question from, okay, Rachel, thanks so much. Do we have any other person with a question before we complete? Yes, you can ask any question. You can also unmute and ask the question. Yes, we have Faith, Lillian, you are too silent. You also have Lucky. We have Megan Osewe. Yes, you are so many today. Then we also have another person here. What's his name? Yes, your name is not coming very well. Yes. So if you have any question, you can be able to ask it before we get to the end of the lesson. Okay, so if we don't have the questions, that marks the end of our lesson today. We shall also meet, that is tomorrow, to discuss much. But do not forget about the little quiz that we have for today. The quiz will also be posted on your WhatsApp group so that you can be able to try. In the beginning of the next lesson, we shall be able to work out the answer to that quiz. So see you next time and have a very nice day.